I sort of felt bad that Mike had such a long title and I had a much shorter one, so I added to mine, okay? But I was really struggling, on what to call this, because it's basically a question really on this particular topic. It's a question of two things: a valid approach, and what we tend to struggle with more is the variance that goes with it, okay? And so really it boils down to, I started with my stick is bigger than your stick, but that seems sort of aggressive, okay? And so I'm not sure if rock's better, but at least we build houses and walls out of rocks, okay? We don't just throw them at other people, but my rock's bigger than your rock, plus or minus 200%, okay? Not a very helpful measurement, is it? Okay, so think about variation as we go through this. And, as Mike pointed out, we do know that the cows have requirements for amino acids, and we understand more about them now than we did 20 years ago. Do we know everything about them? No. But, at least there's 5 that I feel, fairly comfortable that we have enough data on to make use of. And they're likely all sort of plateauing responses, but at least within the range that we have in the literature, they all exhibit more linear responses. And so I think that's what Mike was showing you a minute ago with, if we add a bunch of methionine and amino acids to these diets, these cows will go up on milk protein. It's a question then of, is it a economic return, okay? In other words, it's not cheap always to add those. So we have these that we can use, the availability, or the reliability of those predictions when we use these 5 amino acids plus energy in an additive and non-exclusive manner. So in other words, not using this idea of a first limiting concept, halved our errors of prediction, okay? It's like night and day difference, okay? I know that we've, had this barrel and stave for 100 years, and we understand it. It's simple. We can explain it. Everybody in the world has explained it to the students, but it's not the right concept, okay? So you got to abandon that. And it doesn't really matter if you use direct grams of metabolizable amino acids or if you use them as a ratio to energy, as Mike was showing with the Cornell model. The performance of those models is about the same. There's a little bit of statistical worry about doing ratios because that's violating the principles of linear regression. But at any rate, it does work, okay? And this system works way better than it did before, so you should have some confidence that if you get the amino acids into the animal with enough energy and sort of a reasonable mix of them, they don't have to be perfect, okay? You don't have to be sitting there spending hours trying to get it down to the last, 4th decimal point, okay? Get it close and they'll be fine. And if you add more, they will respond. And then you just have to ask, was that a good economic decision? Okay. So what I'm going to focus on then is, how do we assess whether we're getting it into the cows? And I'll focus mostly on, of supplements like rumen-protected amino acids, but the questions are all the same for ingredients, okay? And the issue is that we're putting things into the front of the cow, and we would, of course, like to know how much are we capturing in the milk, right? What's our availability of that? Well, there's a lot of stuff in between absorption and milk, okay? There's a lot of complexity here. And we do our best when we're doing experiments, if we're trying to measure our availability, from mouth to milk, to try to get those cows all managed to be equal as we go across the treatment so that we can sort of do this by difference. Well, we aren't always super successful, right? And not all the cows behave, and not all the cows are the same to begin with. And so we get quite a bit of variance in that. So other options are, and an original option was, okay, well, how about if we measure by putting a cannula in coming out of the rumen, and then another one into the end of the small intestine? Perfectly valid approach. Best you're ever going to see on stats for doing ileal minus duodenal or duodenal minus ileal, about 30 to 35% error, okay? So if I tell you my rock weighs 5 pounds, it's plus or minus 30%. And so if you're trying to compare my rock to another rock that weighs 25 pounds, well, you don't know the difference, okay? And so that's an issue with that technique, and I'm not going to talk about it. It's a perfectly valid technique, But until we come up with some better methods of making that measurement in terms of markers and so forth, we're not going to gain anything on that, okay? We can gather another 700 observations in the literature before the next 20 years, and we still won't probably make any more progress. You can look at it appearing in the blood, right? And so there's a couple methods that we use to do that. And that's, again, a very valid approach if done correctly. And it seems to be a little bit more lower levels of variance. And then, of course, the one I've already referred to, we can look at it appearing in milk and try to manage the cows for that. So let's look at each of these briefly. So I'll start with the milk first because it's the easiest one to think about, right? We do two diets. We got one diet, where we have our no amino acid added, and then we got another one where we have the amino acid added, and we need a measuring stick. So we make the measuring stick by infusing the cows with varying amounts of the amino acid of interest. Now, this is not really something that I can see how you could do on an ingredient. Like if you wanted to know what all the essentials were out of soybean meal, you'd have to do 10 different experiments, okay, I think. Or maybe you could get by with 5, but you could not do them all at once, I don't think. But anyway, we do an equivalent of a standard curve. We do increasing amounts of, in this case, methionine. This is out of the literature. And then we look for responses in milk protein. So we got to make sure our cows are fed slightly deficient in protein so that they will respond, okay? I just told you before, I think they will keep responding because that genetic potential is so high, so that may not be that big a worry. But we have to get them to respond. And in these finished cows, they did tend to respond in a non-linear manner. I don't know if that was real or not, because you can see there's quite a bit of variance around that line. And in fact, the variance is roughly about 13.5 grams of milk protein. So if I'm going to put in plus and minus amino acids, if I don't see at least a 13.5 gram response in milk protein from whatever I put in, I won't even be able to tell it from background at all. And in fact, we need to get 2 standard deviations. So I need to see a 26 gram response, roughly, to get up to a probability of 5% that I do have an estimate of that. It's one thing to know that it's different from 0. It's quite another to know that it's 70% plus or minus 5 or 10 is what we're looking for, okay? So now I even have to go more than that to try to make use of this. And so I've provided some calculations here that I don't want to belabor a lot, but basically, if we've got a 20 gram error on our response curve here, we need to get 2 standard deviations, so we need to have a delta of 40 minimum, and then we're going to have a delta greater than that to be able to get our error on our estimate down enough that you have any faith in it in terms of comparing one product to another. So you're probably looking at really needing to, when you use this method, having a delta for methionine going into the cow on your product, metabolized methionine, of 60 grams. If the product delivers 60%, then I've got to have 60 divided by 0.6, right? I got to have 100 grams going in. So we got to put quite a bit in. And then you start worrying about, okay, well, that might knock intake because they are sort of toxic at high levels. And so we start worrying about that. So, and then you have to think about that this is the standard curve and I still need to do my product, right? And so what if I choose 80 grams for my product? I've got to have a standard curve that goes beyond that, right? Maybe not beyond 80 because I doubt the product will be 100% bioavailable, and it certainly won't be more than 100%. But I have to think about setting that up. And it's really difficult. I mean, you have to use a lot of cows to get reasonable stats on this, and you could. The problem is our standard curves developed with infusions. Well, that's expensive, okay? That takes a lot of time and effort. It's not easy to do these infusions. So I don't know. It's not a great method just because of the variance on it. What we're doing is we're trying to do similar to this, but without trying to avoid doing the fusions. And we've got quite a bit of work to do yet. But one of the things that we're looking at is, can we actually use these robotic feeders and then a couple of different grain mixes, and then use a mix of those grain mixes to run the amino acid of interest up and down. We can only do 1 or 2 at a time, depending on how many bins you have. And so this is just actually some MP responses. And so this is the average response across 50 cows. And then we picked out a high responder and a low responder. There's quite a bit of variance among the cows. The key part is the error on this is not super bad. And if we could get away from doing infusions, Now we could do 100 cows or 200 cows or 500 cows. And we can shrink that error down where it becomes a very precise measurement for us. So that's sort of the direction we've been working more recently. Let's move then to another method. Let's move back into the blood. And there's a couple ways of doing this. One that's been done sort of historically came out of France. Henri Rocan did this and published it in 2003. We've sort of known from rat data back in the 1930s that when you overfeed protein, the more you feed, the higher the concentrations of amino acids in blood become. And in fact, when you do that, and this is methionine on the left and lysine on the right, as you increase, well, I'm sorry, they published this, you know, if you were a grad student, you know, of one of ours and you published your graphs this way, we would slap you, okay? It's the independent variable is the infusion, so that should be on the bottom axis, all right? So turn your head sideways, think about increasing amounts of methionine from 0 to about 30 grams per day, and then the dependent variable is the blood concentrations, and so they're looking at expressed as milligrams per 100 mils of plasma, and you can see that they got nice tight linear curves across the 4 cows, fairly tight statistics, and they got about an 8-fold response range, which is really good, okay? We go over to the lysine, and they infused a bit more. They probably should have done more because lysine is roughly twice the input that methionine is. So perhaps they should have done some more, but you can see that all 3 of the cows responded linearly, same general slope, but huge differences in the intercept among those. And when we've done these trials with lysine, we see exactly the same thing. And so for a long time I puzzled, you know, why do we get these big responses and very tight statistics from methionine? Well, again, you know, I had to change jobs every so often, so I'm not the brightest individual, so it took me about 20 years to figure that out. Methionine is a DL mix. The D can't be directly metabolized. It has to be converted to the L. And that's a very slow process for methionine in cows. And so we end up seeing large concentration responses to these DL mixes when we put them in because the D is building up. It can't convert it fast enough, and so it just keeps going up and up and up. And yes, it does eventually get it converted, but it drives up the concentrations a lot more. That gives us these nice tight curves and nice tight stats. Lysines, it's just L. It's got about a 20-minute half-life, okay? So you got to put a lot in to drive it up. And that's why there's a lot looser statistics on those. So Henri did that study, and then they followed up, after they demonstrated they got linear curves and had their response curve. So I should back up. So you can then come with a product, and you can feed the product, right? And you don't know what this availability is, but you can read what the concentration is, and so you can extrapolate off the curve and say, okay, it went up by this much, therefore I have this much methionine that's being delivered to the animal. And so they did that with the SmartAmine ML. And so they had both methionine and lysine data. They did a couple different goes at it, and essentially what they came, and you might guess this from the standard curves that I showed you a minute ago, was the methionine error on the estimates from plus and minus and different, actually they used 3 different concentrations in the one study, was 10%. Well, that's good, okay? Whenever we can get a biological measurement plus or minus 10%, we're in pretty good shape. The lysine is 18. And when we did the same kind of things a couple times, we got exactly the same number. We got 18%. We couldn't get it below that, okay? And I think that comes back to if we were putting a DL mix in and assuming the D could be converted in lysine, we probably would have better stats. We can maybe get that if we put a lot more in. And we tried doing that, and we did cause, at the highest level, depression in feed intake in cows. Okay? So they won't tolerate huge amounts of these. I mean, they'll tolerate quite a lot, but we can't just keep putting it in to try to get us a big enough measuring stick to get our variance reduced. Okay? The cows just won't take that. So a perfectly valid method. It works. It's a question of getting your stats good on the non-methionine ones. Okay? The methionine actually works quite well. So the last sort of general approach with 2 different sort of applications is efficacy by dilution. And so the idea here is that if we were to say we had a highway and for some reason we couldn't actually directly count the cars going by, okay? We have to somehow figure out an indirect method to figure out how many cars are going down that highway. So we got cars entering up here, and basically there's a mix of these non-white cars and a few occasional white cars. And we go and we get all of our students, right, and we go rent all the white cars from Enterprise and Hertz and everywhere else we can, and I line them up on the on-ramp, right, and I say, okay, here's your stopwatch. Each one of you got to enter one car at a time onto the highway, you know, in that white car. And then drive like crazy, okay, so you get all mixed up in here, and then I'll go downstream and I'll count the ratio of white to non-white cars. So by difference then, if I know I have 1 per minute going in, if I have 5 white cars and 10 non-white cars, well then I know for every 1 white car that entered per minute, I've got 2 non-white cars coming down the freeway. Okay, so a very simple thing. So we can do that, and then we can add our unknown product in, right? And so in theory, it's adding more non-white cars to the freeway. We're going to continue to put our white cars on 1 at a time, or 1 per minute. And so we can see in this case, we've got a greater ratio of non-white cars to white cars, right? And so we have 3 cars per minute going down the freeway. And so that's our measuring stick for how we do this with looking at these amino acids coming into the blood. This can be applied to all of the amino acids at once, okay? That we can, at least the essentials. And this is sort of the concept that Bill and Norman used with the selenomethionine. So sort of nice of yeast that once in a while they add a selenium into the methionine when they synthesize it rather than using the normal sulfur. And so when they do that, they end up, when we feed yeast to the cows, they'll actually take some of that selenomethionine, and the mammary doesn't know any difference. They'll make it into milk protein, and we'll get selenomethionine into milk protein. So we can measure the selenium, or we can measure the selenomethionine, and they did it both ways. And then we can do our experiment again, plus and minus, right? And so they had, plus and minus 10 grams or 9 grams of methionine. Now, I've made that mistake a couple times. 9 grams of methionine is never going to be enough, okay? They are obviously much better at doing this than me because they got almost exactly 9 gram response, okay, in their measurement. If I did that, there's no way I would have gotten 9 because it's 9 plus or minus 43%, okay? So they obviously were very careful how they did it, and they were very lucky that day. And they got the right answer. Nothing wrong with the technique. Put more than 9 grams in, okay? You need to put 20 grams or 30 grams in, and you'll get a pretty reasonable answer. But you do need to use quite a few cows because this is not, you've got some variance across cows. And I think that's where we see some of the variance when people are doing these estimates, is they're just not using enough power, basically. And it doesn't really matter. I didn't make this point. I probably should build this different. But essentially, we can have cars coming on ramps everywhere as long as they're all mixed up before we get to our counting point. So it's just sort of a question of how we do these experiments. I'm going to skip this because what we do is we use isotope. So we isotopically labeled amino acids rather than the selenomethionine. We don't have a selenolysine or a seleno anything else. Maybe selenocysteine, but so that's the only one we can use that with. So what we do is we get our friends at Cambridge Isotope or at Sigma to make us up a batch of they'll grow algae with C13 CO2, and they'll get all labeled up with C13, and then they'll hydrolyze it and clean it up. We infuse those, and so we can then look at most of the essentials. Okay. We have some trouble getting histidine, and we can get that. You have to supplement a little bit. Methionine's okay. We don't get cysteine. It's a non-essential anyway, so we really have to focus just on the essentials. And our analytical technique destroys the arginine, so we don't get that. So we get the other essentials other than arginine. And so this was Carrie Estes' master's work, and so there was a question of what the value, biological or bioavailability of the essential amino acids. And more importantly, they were interested in the RUP and the protein, what it was worth or what it was valued at in the marketplace. And so we're looking at blood meal and feather meal. Okay, so it was poultry, basically poultry study. Poultry industry funded it. And so you can see here that the two products, the feather meal is in red and the blood meal is in black, and the data are expressed, for each of these amino acids as a percent of the amino acid that was in the product, okay? So we're talking about delivery to blood from product. So through the rumen, we've got some ruminal degradation, we've got some indigestibility in the small intestine, and there's a little bit of loss during absorption, which we correct for that to try to get it back to an absorbed value. And so you can see that, we had roughly 50% here, it depends on the amino acid, and our error bars are fairly narrow. Now, I have to say we were somewhat lucky that we chose those two ingredients because they're pure protein, and when we added them, we could get the cows to tolerate about 20% of their dietary protein as that, and that helped us squeeze these errors. When we look at low protein ingredients like corn or even some of the hays, because they have poor RUP values, our errors explode then because it's an absolute error, and when we start dividing through by a small number, it becomes much larger. But in general, we can usually make 10 to 15% errors if we use 6 animals with 6 observations, or 6 periods. So it's a pretty precise way of doing this, so we're getting more towards the numbers we want. And so we've screened a lot of different prototypes for different companies. We've published a couple papers on ingredients, so that we had some values for that. The one ingredient we failed on a couple times is soybean meal. You would think that would be easy, but eventually, we'll get that one published. But this is, products that we did for Balchem. So the AminoSure is on the market, and our plasma appearance, and then correct in the other column is correcting for that roughly 7% loss during absorption. So it basically has a 55% bioavailability. They have a couple other prototypes we've tested for them that are 64 and 47, so better and poorer. Again, plus or minus 12, 13%. We can't necessarily always tell the difference between those. And then we've tested a couple histidine prototypes for them. One's very good, okay? 73% is pretty good. We just need the histidine to get a little cheaper yet because it certainly has good value in terms of making more milk protein. So, in conclusion, there's several valid methods, okay? We hear this bantied about what's the gold, standard. Well, there's like 4 gold standards, okay? You can do this about 4 different ways, and they're all valid. The biggest problem we have is the variance on these. It's not the validity of the measurement, it's the variance. And so we just need to bite the bullet at times and spend more money and do more observations to get our variance under control. And there are some methods that generate less variance than others. So we can also help ourselves if we feed more of whatever we're trying to assess. Okay, we don't certainly giving 9 or 10 grams of methionine. That's just foolish. Okay, you're not going to get a good solid number out of that. We need to bump up the amount that we're feeding. We can certainly look at it in blood concentrations, and I'm trying to give some sort of guidance on how much we need to use, because you can back calculate and say, okay, well, if this is my variance in my measurement, this is how much delta or how much deviation I need to have when I do minus and plus, right? And we need to use that when we do it. And so each one of these 3 methods have, slightly different variance. So what's the take-home message? Okay, there are 3 methods that are valid and effective. What you need to be asking as nutritionists is, show me the data. Okay, because we've certainly tested, and I forgot to make that point. We've tested some products that have really good ruminal protection, and when those are lipid encapsulates only, they're almost always very good small intestinal protection as well, okay? They go right through the cow, all right? So you need to see the data, okay, and pay attention to the standard errors on it. If they're showing you data and it says it's 60% bioavailable and it's plus or minus 30, well, it could be 30 or it could be 90, okay? It could be really good or it could be really, pretty marginal. So look at the data, okay? And checklist for using these. Every once in a while, I still see somebody when I go on farm that I've got product X and this lipid encapsulated amino acid in my diet, and I'm looking, and it's all pelleted. Okay, there's no loose grain. Okay, none of these withstand pelleting, with the exception of Metasmart, the isopropyl derivative of HMBI or HMB. That one's the only one you can pellet. The rest of them you cannot pellet, okay? These are fragile coatings. They won't hold up, okay? Don't overmix, right? Don't let them mix in the mixer forever, okay? They're going to be abraded, and you're going to cause problems with the coating on it. These got to be treated very well, okay? I remember we had a stats professor at Iowa State, which was very good, strong in stats, and a little sort of short Indian woman. She goes, "Statistics are your friend. You should treat them very nicely because they're very important in your life, okay? These are the same way, okay? Treat these nicely. Avoid long feed exposure times. That moisture in the feed and the acidity in the feed tends to start to degrade that coating, okay? So you don't want to let it sit, maybe 2 times a day of feeding might be somewhat better than once a day, okay? I don't know. We really haven't done a lot of those experiments yet. And, obviously the normal laundry list, if you're not getting a protein response or a milk response out of these products, and you've checked all the list above this, then look in the mirror, okay? It may be cow comfort, it may be heat stress, it may be all these things that you normally are going to look at, okay? If it's being delivered to the cow, it should be generating a response, okay? All right, and of course, dietary energy is a big part, okay? We cannot feed a low energy diet and expect cows to perform.